So looking at this last example that we did at the top of this page, we showed algebraically at the top of the page that this is an identity. Okay, we know that whatever angle we want to plug in on the left and the right, we should get out the same value. Okay, now let's say, for instance, that you didn't want to go through the proving process, okay, the work that we did at the top of the page. Maybe you thought just testing a value would suffice. Okay, maybe you just wanted to plug in a number to see if it would be the same on the left and the right. I have to caution you though about that, because maybe there's only one number that would work and you just happen to choose that number. Okay, just because it works for one number doesn't necessarily mean it's going to work for all the other radian values on the unit circle. So that's why we have to go through it algebraically, okay, by keeping it in terms of trig functions, because if we can do it that way, we know it's going to work every single time. Okay, but kind of to play devil's advocate here, let's say I didn't want to go through the algebra. Maybe I just wanted to pick a radian value. Okay, maybe in this instance, pi is the first one that popped into my head. We want to try to figure out or think about why this particular radian value would not be a good one to pick. Okay, if we are going to pick a number, we have to make sure it's a very strategic number that we pick. Now, if you think about pi on our unit circle, a whole circle is 2 pi, so half of that is 1 pi, so that's the leftmost point on this unit circle. And if we think about the ordered pair at this point on the unit circle, our cosine value, aka x, is -1, and our y, aka sine value, would be 0. Okay, kind of just like on a coordinate system. So let's keep that in mind. If I were to plug in pi in for all of these angle measurements, let's kind of see what would happen. So cosecant, we know, is 1 over sine. And then on the right-hand side, we get to cotangent, which is cosine over sine. Okay, so using this ordered pair, I'm going to go ahead and plug in the specific value. So the sine value at this pi location, okay, maybe I'll do a c comma s, okay, cosine comma sine. The sine value is 0. All right, so for every sine, I'm going to throw in a 0. And the cosine value is -1. So for every cosine location, I'll throw in a -1. Now, if you were to actually go ahead and try to solve this, hopefully you realize something tricky is going to happen, because we actually have two spots where we have a 0 in the denominator. And we know we cannot divide by 0. So when I say you can choose any radian value you want to test it, okay, technically that is true. You can choose anything you want, but realize that some radian values, when you do try to test them, might not actually help you verify that the left and the right are the same. And this is a good example because we cannot go any further on the left or the right because of these undefined values. Okay, we cannot divide by 0. So let's go ahead and explain why this radian value is not appropriate. So we'll say the theta value of pi is not a good choice because it leads to an undefined result. Okay, we eventually want to show that we get a numeric value on the left and it matches a numeric value on the right. You can't really match undefined results. Even though they're both undefined, they actually might be different types of undefined. For instance, I could have 0 over 0 on the left, and maybe I have 4 over 0 on the right. Okay, even though those are both undefined, they're really not equal to each other. And if we think back to when we did rational functions before, this is actually signifying a whole, where this one is signifying a vertical asymptote. Okay, we can have different types of undefined values. So we have to be careful on which radian value we pick. Okay, just like as we go through the algebra of the solving or the proving, if you do come across a roadblock, just try something else. So maybe I wanted to do pi, it eventually led me here. I know I can't quantify undefined values, so maybe next time I'll try pi over 2, or maybe pi over 3. Okay, just choose something different to test it. All right, so I just wanted to touch base with that to kind of show you a numeric way to kind of verify your work, but be careful about it in the process. All right, let's try a few more. We're going to go ahead and take a look at what you think is the more complicated side. And when I look at this first one, I definitely think the left is more complicated. So I'm going to go ahead and work on that side and show that I can get tangent on the right. So secant is 1 over cosine. Cosecant is 1 over sine. And cotangent is cosine over sine. Again, I'm only working on the left-hand side. So let's see how we can simplify this. In our first parenthesis here, I want to add two things together. One of them happens to be a fraction, so somehow I have to get a common denominator. And I can easily turn the number 1 into cosine over cosine. That way the denominators match. In our next parenthesis set, I notice how I'm subtracting two fractions together, and their denominators already match, which is great. So I'll go ahead and subtract the tops and keep the bottom. All right, we're going to go ahead and kind of do the same thing for this first parenthesis. Now that the denominators are the same, I'll go ahead and add the tops, but keep the bottom. All right, let's see where we can go from here. So both of these fractions are as simplified as we could possibly go, but notice how they are being multiplied together. Okay, we have this first fraction times this second fraction. So we're going to have to multiply the tops together and the bottoms together. So when I look at this, I can easily multiply the bottoms together. That's cosine times sine. But if I want to multiply the tops together, I'm going to have to go through some type of FOIL or distribution process because I have two terms times another two terms. So I'm going to go ahead and do 1 times 1, 1 times negative cosine, cosine times 1, and then cosine times negative cosine. So that would be a negative cosine squared. So that gets rid of the multiplication. So we have one gigantic fraction now, and we're praying that we can eventually simplify it to match tangent. So when I take a look at the numerator, I notice how I have two cosines. They're opposites of each other, so those will cancel conveniently. And I'm just left with 1 minus cosine squared up top. Hopefully, we have that little light bulb going off when you see this numerator. That's a manipulation of our Pythagorean identity, and we can simplify that to sine squared. Now that's essential because notice how if we have two sines up top being divided by one sine on the bottom, we can cancel a pair of those out, and we'll be left with one sine up top and a cosine on the bottom, which we know is equivalent to tangent, which is exactly what I wanted to prove. All right, looking at our next one, think about which side you think is more complicated. If you think they're equally complicated, maybe work a little bit on both sides. It's completely up to you. Let's see, tangent I'll rewrite as sine over cosine, cotangent, cosine over sine. You know what, maybe I'll just work on the left-hand side. If I come across a roadblock somewhere, maybe I'll start to work on the right. So I have these two fractions, I want to add them together. In order to do that, I need a common denominator. So I'm going to take this denominator of sine, multiply it on top and bottom, this denominator of cosine, and then multiply it on top and bottom, Please excuse the software. Sometimes it has to catch up to my writing. All right, so for our first fraction, we have sine squared over sine times cosine. For our second fraction, we have cosine squared and then sine times cosine on the bottom again. Now that we have that common denominator, we can go ahead and add the tops and keep the common denominator. Okay, let's keep in mind that our ultimate goal is to get secant times cosecant. All right, hopefully we have another light bulb moment. Sine squared plus cosine squared is 1 using our identity. And notice how if we have these two terms on the bottom that are being multiplied together, I could technically break apart this fraction with multiplication, keeping the denominator of the numerator of 1 up top the same in both. Now, this might be a little tricky fraction work here, but if you actually think about it, maybe work backwards to see why it makes sense. If you multiply these two singular fractions together, you will end up with this left-handed side. Okay, multiply the tops, you get 1. Multiply the bottoms, you get sine times cosine. So you can break up that fraction in this manner, and hopefully that's going to make it a little bit more obvious as to why it's going to match the right-hand side. Because 1 over sine, aka the reciprocal of sine, is cosecant, and 1 over cosine, aka the reciprocal of cosine, is secant. So I have cosecant times secant, which matches what I have at the top. The order's switched, but remember, order doesn't matter when you multiply. So we are good to go. All right, last but not least, take a look at the one at the bottom and think about which side's more complicated. I definitely think that's the left side. So when I take a look at this left side, I have this fraction minus this fraction. It's already in terms of sine and cosine, so I can't really rewrite anything. What I'm left with is fraction work. So I'm going to have to get this denominator and this denominator to match. And maybe you've seen some strategies to help you with that up to this point. We want to take this right-handed denominator and multiply it by the first fraction on top and bottom. And then we're going to take this left-handed denominator and multiply it by the second fraction on top and bottom. Keeping in mind our ultimate goal is to get 2 times tangent. So from here, we have to take this fraction, oops, I'm moving the screen, there we go. Okay. We have to take this fraction times the next one, so multiply the top, multiply the bottom. If I distribute in the cosine, I'll get cosine plus sine cosine. And if I distribute the two quantities in the denominator, I'll get 1 minus sine plus sine minus sine squared. Okay, going through some type of FOIL process. We're going to do the same thing for this other fraction. So I'm subtracting. Let's make sure that we don't forget that. I'm going to go ahead and distribute in the cosine. So cosine minus sine cosine. And again, go through some distribution or FOIL for the denominators. 1 minus sine plus sine minus sine squared. My time's going to run out in a little bit, so I'm going to stop it here, but continue with it in the next video.